differential equations in the real world. Well, when you think about it, most differential equations are for real world problems anyway. A tank has 30 litres of solution of chemical. Concentration of the chemical is reduced by pouring pure water into the tank, and it's going in at 1 litre per minute, and then the solution runs out of the tank 2 litres per minute. The tank contains X litres of chemical at time t. Show that dx to t is this expression here, and it's a mixture of x and t. So how did I do this one? Okay, well, every minute the volume of the tank is reducing by 1 litre. So we know that. Thus, in t minutes, we know the volume of the tank will be 30 minus t, because it starts with 30 litres. Now, at time t, the fraction of solution that is chemical then must be x over 30 minus t. So x over 30 minus t. So that's the fraction of solution. But the solution is escaping at 2 litres per minute, so therefore our rate must be 2x 30 minus t. We have our equation. We want to find the fraction of the original chemical still in the tank after 20 minutes. I don't know what the original volume is, so I'm just going to call it V. dx to t, we just found out, is minus, because it's going down, 2x on 30 minus t. Separate my variables. We know when t equals 0, the volume, I've now just called it V, and we want to link x and t together. I suppose I could have just thrown 20 in for t there and got x straight away, now I think about it. Anyway, it doesn't matter. So left hand side we have a log function, so we also have a log function on the right hand side as well. So the log of x on v, when I substitute in, will be 2 log 30 minus t on 30, which means x on v is 30 minus t squared on 900, making x the subject. We want when t equals 20, we end up with v on 9. Now I don't know what v is, but I don't need to know what v is, because the question was find the fraction of the original chemical. So we know we've got 1/9 of the original chemical, whatever the original amount was. Population of foxes. There's our logistic equation. Mind you, we're going to do this a little bit differently, because they're going to tell us to use this substitution. Y is equal to 1 on 1 minus W. And the reason they've done that is it's going to allow us to transform this differential equation into something very simple. dW, so dW dt is negative W. So this is what we're going to do. So y is 1 on 1 minus w. That's the substitution they've asked me to use. Let's work out dy to t then. So dy to t, if I do it implicitly, differentiate 1 on 1 minus w, so minus the derivative on the function squared, we get 1 on 1 minus w squared, but times that by the w to t. Now I'll use the fact that dy to t is y 1 minus y, substitute into that. Okay, a bit of algebraic manipulation, but yeah, we get it to be minus w, which is what they're looking for. So now we're going to use that to find the solution of the logistic equation, and the initial conditions when t equals 0, y is a quarter. But we're now playing with w, so I need to work out what w is, and we get w is minus 3 at that time. There's my new differential equation. The w dt is negative w. That's our basic growth and decay. So I can just jump straight to the solution now. So w is minus 3 e to the negative t. So y is 1 on 1 plus 3e to the negative t. Remember, because y was equal to 1 on 1 plus w. There is the solution of our logistic equation. So how long will it take for the fox population to reach 3/4 of the carrying capacity? Well, now I'm just solving an exponential equation. The one I've just found has to equal 3/4. Playing around with that, eventually we get, so e to the t is equal to 9, so t is log 9, 2.197. So 2.2 years to reach 3/4 capacity. Alright, something far more relevant for you guys, maths in the real world. I just made the numbers a little bit nicer. A rumour is spreading amongst 1,000 students in the school. Okay, we've got about 1,200, but 1,000 makes the maths a little bit nicer. So 1,000 students in the school at a rate proportional to those that have heard it, but also those who have not heard it. Okay. As time progresses, people care less about the rumour. So the proportion rate is not constant, because that's what happens with rumours. That's what goes on, we don't care. So the rate the rumour spreads can be modelled by this logistic equation. dx to t is equal to some constant x 1000 minus x over t plus 1. Now if initially one student starts spreading the rumour, because that's how it starts, one student spreads the rumour, after 1 hour 50 students have already heard the rumour because they were using their phones in class and they shouldn't do, and it's got out there. How many students have heard the rumour after 3 hours? So half the day has passed. How much of the school have heard this rumour? Like, this will be in the test. There's our equation. Separate out my variables, and we said when, what was it? T equals 0, 1 person, so 0 and 1, and 1 and 50, so we can work out what this k is. Okay, well, left-hand side, partial fractions, we can get it 1 on x plus 1 on 1000 minus x. Subbing in, there's our constant. I don't want to have to write that every single time in my working out. I'm just going to leave it as k in my working out, but that's the number I'll substitute in for k. We now want to find x when t is 3. Notice still the same integral, so I already know the answer and everything, so I just went straight to that. So the left hand side here I've just called c. Okay. So c will equal 1000 times log Alright, so now, 99x on 1000 minus x is e to the c, and eventually there it is. Whoa, look at that number. 734 students have heard the rumour after 3 hours just because one person came up with a rumour. Alright.